Okay, let's go ahead and start the class. Let me. If you haven't picked up one of these handouts here, the exam review problems, make sure to come to the front and pick one up. Today, as you all know, we are going to. I don't know what's going on with this camera. Okay. We are going to focus on the exam 2. We will do a small review of exam 2. I'm actually thinking of solving some homework 4 problems as well. Let me just bring it up. Now we have homework 4 here. How was the homework 4? Okay. Did you have any questions or problems? No? None? Okay. If there is any of the problems you want me to work on, please go ahead and bring it up. Mention it right now, and we will work on it. I'm going to focus on what was the problem number? Problem number 8, and also number 4. These are the 2 problems that we will. I already received comments that people need me to focus on a little bit. But let's just start talking about exam 2, and then we'll get to the problems. So exam 2, as you all know, is going to be given on Thursday. This Thursday, that's Thursday, April 15. You will have 75 minutes. Pardon me? Wouldn't it be the 15? What did I say? This is 15, but I guess there are some leftover chalk. April 15. And there will be, I don't know if we talked about this or not. There will be, I don't remember how many I said in the previous lecture, but 3 to 4 questions like explanatory questions, explanatory questions that you need to explain the answer, and there will be 3 problems that you need to solve. Problems that numerical problems. Let's call them numerical. Okay. Is there any questions or comments or concerns about the structure of the exam? No? Is it going to kind of be like the last one? Is it going to kind of be like the last one? It has fewer questions, right? What do you mean by that? Like, I mean, like it had, like it's pretty much the same thing. Like how the first part was more the definitions and stuff. Yep. Yeah. You'll get the definition questions at first, and then you'll get to the problem solving. That just answers my question. Okay. So yeah, problems 1 through 4, for example, will be these questions, and then problems 5 to 7 will be these problems. And most of the problems that you are going to solve in the exam will be just very short answer problems. You just use one equation, plug in the numbers, and you get the answer for it, right? or 2 equations maximum. You just have to make sure you understand the concept so you can find the appropriate equation to answer. Well, what I've done here on these handouts is that I've gone over the lecture notes, and I have wrote down all of the conceptual problems you can get out of these 3 chapters, right? So there is no more concepts. This is all, right? There's nothing more. And you have to be able to define the Eulerian methods versus the Lagrangian methods, which was in chapter 4. You have to be able to understand what's a steady flow versus unsteady flow. You have to be able to define streamlines, streak lines, path lines, and you have to be able to tell me when they are the same. If you have no idea about any of these questions, you can ask, and I will provide the answer right now, okay? But all of them are provided in your lecture notes. You don't have to. I just went over the lecture. I took these out of the lecture notes. So if you have the lecture notes, which you can have, you can just download them from Blackboard. You will find the answers to these questions. You have to know what's the equation or how to find the equation of the line for a streamline. You have to know what is the material derivative, what are the 2 types. Take a handout. You have to know what is the material derivative, what are the 2 parts of material derivative, and you have to be able to tell me how do you calculate acceleration of a fluid particle, what is the equation for it. You have to be able to explain what are the streamline coordinates. You have to be able to define control volume and a system and tell me the differences between the 2. You have to be able to write down the Reynolds transport theorem equation and explain to me what it does. You have to be able to write down the integral form of conservation of mass, momentum, energy equation for a fixed or moving control volume. Just have to include those in your equation sheet, and you, as long as you know which equation is which, you should be able to answer those problems, right? And what does moment of momentum represent? That's another equation, which is simply angular momentum, right? And you have seen this in your dynamics as well. And just write down the equation for it. No calculation, just write down the equation. How can you find the dimension? So there's an error here. It is supposed to say, how can you find the dimensionless parameters? And then the next one is, what is the Buckingham Pi theorem? The next one is, why is the dimensional analysis or use of dimensionless parameters important? Are these questions, do these questions sound familiar? Do you feel like you have seen them before? Right? All of them are definitely there in the lecture notes. So what I've done, I just went over all of the lecture notes. Whatever question I could design, the conceptual, I wrote it down, right? So if you can answer all of these questions, you essentially know all of the concepts you need to know out of these 3 chapters, okay? Which is, I guess, a very important achievement. So one thing I forgot to mention, the same as previous exam, you can get a 2-sided letter-sized or A4 size, doesn't matter, equation sheet. Okay. Any questions so far? Okay, who can tell me, let me ask you this, who can tell me what was the difference between or what were the Eulerian methods Eulerian perspective and the Lagrangian perspective. Who remembers that from chapter 4? Any question you answer yes. Exactly, exactly. So Eulerian was the second thing you mentioned, like using a control volume, right? Or a system, and Lagrangian was falling apart here. Could you do me a favor? Can you write down your name on a piece of paper? And let me do the back of this. So whoever answers my questions this lecture will get a bonus point, right? Okay. The next one is that I want you to answer me is that how can you find the dimensionless parameters? That's question I. What are the methods we have that you can employ to find the dimensionless parameters? We specifically learned of one method, one methodology. That's the question I on the handout. How can you find the dimensionless parameters? No, no, no. That was the Reynolds transfer theorem, right? Yes. That's it. That's it. Exactly. Buckingham Pi theorem. Thank you. So what was your name? Noah Jefferson. Noah Jefferson. Noah Jefferson. Okay, so let's actually start solving these problems. I will ask more questions during the lecture, and whoever answers those questions will, of course, get a bonus point. Okay, so we are going to start with the problem 2 on your handout. We are told the two-dimensional velocity field is given by u is 1 plus y, and v is 1. We want to determine the equation of a streamline that passes through the origin. And we want to plot this a streamline on a graph. So equation of a streamline that passes through the 0 and 0 points, origin. The first question you need to answer, and this is something that you had on the homework as well, right? How can we find the equation of a streamline? What was the equation we had for it? We had one equation that gave us the slope of the line, right? Or dy dx for a streamline. So dy dx was equals to v divided by u, right? So two velocity components. We plug in y, v is y, divided by 1 plus y, right? So this is the slope of the streamline. Right? By having this equation, how can we find the equation of that line? You have the slope of the line, which is essentially the derivative of that function, right? And we want to find the equation of that line. In this case, we want to find the equation of the streamline, right? How can we find that? It's simple. You just have to take the integral. you first move the dx to the other side. So dy is equals to, let's actually, to make it even simpler, to make it a simpler integral, I'm going to move 1 plus dy and move all the y's to one side and all the x's to another side. Okay. And if I can take the integral from both sides, I have the solution. I have the equation of the line, which is the equation of the streamline. What is the integral of this? It is y plus y squared over 2 equals to x, right? Since this on both sides we are taking an indeterminate integral, just has to be, we have to add a constant. But we are told that this equation passes through the origin, 0 and 0. So using those 2 points, we should be able to determine c. 0, you have to plug in 0 for y and 0 for x, which means that your c is going to be 0. So the equation of the streamline is going to be equal to x is equals to y plus y squared divided by 2. And to plot this, you just have to find a couple of points, and you will be able to plot. It will look something like this. On an exam, I won't probably ask you to plot the equation of the streamline. Any questions? Next one. Sure.
The graph itself or no?
Can you repeat your question?
All right. Okay, so when plotting the streamline, could we use a graphing calculator to show a graph?
Sure, yeah, definitely. But on an exam, I won't ask you to plot the streamline. As long as you have the final equation, you have the answer. Okay, so let's move on to the next problem. Problem number 3 on your handout is we have a velocity field u equals to negative v and v naught y divided by x squared plus y squared to the power 1/2, and v is equals to v naught x divided by x squared plus y squared to the power 1/2. And we are told v naught is a constant, where in the flow field is the speed equal to v naught. And we want to determine the equation of the streamline and discuss the various characteristics of this flow. Okay. The first part of the question is asking us where velocity vector is equals to v naught, where the magnitude of this velocity vector is equals to v naught, right? To answer this question, we first have to find the velocity vector. Velocity vector is, in this case, it's a 2-dimensional vector, ui plus vj, right? U is the velocity in the x direction. That's why we have ui. V is the velocity in the y direction. That's why we have vj. And if we had a 3-dimensional velocity field, we would have had a wk. But here w is 0, so we don't really include that. And how do we find the magnitude of this velocity vector? The magnitude of velocity, which I'm going to use capital V for, is going to be the square root of u squared plus y squared. Okay? And we are told that this magnitude, we are to find the location where this magnitude is equals to V naught. So let's plug in all of these two components. Let's see what we're going to get. U squared is going to be V squared y squared divided by x squared plus y squared. And then we have V naught squared x squared divided by x plus y squared. And this has to be equal to V naught squared. Is this clear on what we did? We are told to ask the location at which the velocity is, the magnitude of velocity is equals to V naught, right? The first thing you need to do if you are given the components of velocity vector, you have to form the velocity vector itself. That's the first thing you need to do. The second thing is to find the magnitude of velocity using those components and set it equal to the value of velocity. Okay. So I'm going to take this V naught out of this equation, out of these two components. So it's going to be V naught squared, y squared, x squared plus y squared plus x squared equals to V naught squared, right? These two will cancel out. And what are we going to get? We can actually add these two ratios. We're going to get x squared plus y squared divided by x squared plus y squared equals to 1. And they will cancel out. We can cancel them out. And eventually, we will conclude 1 is equals to 1. What does this mean? Right? We didn't find any x's and y's. We didn't find a location for which the magnitude of velocity is 1. To find that location, we should have found a set of points. X equals to this, this, and this, and y equals to this, and this, and this, right? But what we found was 1 is equals to 1, which is always true. This always holds true. There is no way you can say 1 is not equals to 1, right? This always holds true. But what does this mean for this equation, for this problem?
Everywhere in the flow field is equal to V naught.
Did you want to say the same? Yeah. Yeah, exactly. Thank you. What was your name? Cooper. So I'm going to give you the bonus as well. Yeah. 2 bonuses. Exactly. So what this means is that since we came to an equation that tells us that your equation, this equation, always holds true, right? This is the result. This essentially means that everywhere in the flow field, everywhere, velocity is equals to V naught. The magnitude of your velocity vector is equals to V naught. So it doesn't matter where you are. If you calculate the magnitude, you are going to get V naught. Is this clear? Okay, so let's talk about the second part of the question. Again, we are told to find the equation of the streamline. We have this equation, this main equation, for the equation of the streamline. Just plug in the components. I'm going to write it here. V divided by U. So we have v naught x divided by x plus y squared to the power 1/2 divided by negative v naught y divided by x squared y squared divided by half. This will cancel out, v naught will cancel out. And for this flow field, we're going to get dy dx is equals to negative x divided by y. Or you can say x dx equals to negative y dy. Okay. Can we take the integral here? Right, to find the equation of the streamline, this was the first step. To find the slope of that streamline, then you simplify your problem. You take all of the y's to one side, all of the x's to another side, and then you take the integral. What will be the solution to this integral? It's going to be x squared divided by 2 is equals to y squared divided by 2 plus a constant value. Right? This is an indeterminate integral. Have to include a constant, and it is negative y. You have a negative sign here. So we move the y squared to the other side. We're going to get x squared plus divided by 2 divided by equals to a constant. We can multiply everything by a 2. It's going to be x squared is going to be x squared plus y squared equals to 2 constant or another constant. Let's call it C1. 2 multiplied a constant, it will be another constant, C1. Okay, what does this mean? What does this mean for a flow field? This is the equation of the streamline. What can you say about this specific flow field? What does it look like? It is a circle. So it will be a circle with a radius of square root of c. Right? Cooper. What else? Let's see what we asked to find. Yeah, we said it is circular flow. And that's it for the second problem, third problem. Let's move on to the fourth one, which I think was on the homework as well. Problem number 4. You are given, again, two velocity components, ax plus bx divided by x squared y squared, and v is equals to ay plus by divided by x squared y squared. And you are told to find the acceleration. It's a two-dimensional flow. We have u and v, components of velocity in x and y direction. So your acceleration will also have two components, ax and ay. If you recall, we said we can find the acceleration of a particle in a fluid using the material derivative of the velocity. So capital D, capital T. Let's find the acceleration in the x direction first. Acceleration is in the first direction is going to be the material derivative of the velocity in the x direction, which is u divided by t. Which is, I'm going to write the most general form of this equation. This u can be a function of time, x, y, and z in the most general term, right? How can we find the material derivative? Partial u partial t plus velocity in the x direction, derivative of velocity in the x direction, or derivative of our parameter of interest with respect to x, plus velocity in the y direction multiplied by the derivative of our parameter of interest, which here is the velocity in the x direction with respect to y, plus velocity in the z direction, w, multiplied by the derivative of the parameter of interest, in this case u, divided by with respect to z. This part is 0. It's a two-dimensional case, so it will cancel out. And your velocity does not depend on time. So partial u partial t is also 0. Okay? We don't have any t term here. It's just x and y. And if you were asked in the exam that what are the two different parts of the material derivative, these are the two different parts. This is the time derivative. This is the convective term, or convective, a local derivative. Convective term or local derivative. These are also in the lecture notes, just in case. So for this specific problem, we only have the convective terms, or the local derivatives. Let's plug them in. First, we have u, so ax plus bx divided by xy squared, multiplied by the derivative of u with respect to x. What is the derivative of u with respect to x? Let me write it here. Derivative of u with respect to x is going to be equal to derivative of this first term with respect to x, a, plus the derivative of this ratio with respect to x, which is the derivative of numerator. Go ahead.
It's derivative by x and one, which is
X.
so that whole fraction together is b over x squared times y squared times -1.
Okay, so b, let's actually do this step by step. Okay, it's going to be the derivative of numerator multiplied by the denominator, right? So bx squared y squared minus the derivative of denominator multiplied by the numerator, which is 2xy squared multiplied by bx divided by the denominator to the power denominator squared. And that's how we did the fractions. Is going to be equal to b minus, that's going to be negative b, right? Negative b, if you simplify it, divided by x squared y squared, as Brandon mentioned. Let me add your name down here. Brandon Sellers, right? Okay. So we have this derivative. Just plug it in here in the main equation. It's going to be a minus b x squared y squared. Next step is v. Let's plug it in here. Ay plus by divided by x squared plus x squared y squared. There's no plus. Multiplied by the derivative of u with respect to y this time. I'm going to take this derivative right here. Derivative of u with respect to y. This first term is going to be 0. The second term is going to be negative 2b x third cubed y, right? Divided by xx squared y squared squared. So just put that in here. Negative 2b x squared y divided by x squared y squared squared. That's it. It's a very long equation, mainly because we are only dealing with parameters, right? Yes. On the exam, I will probably give you numbers. I will ask you to find the, like these equations will be 2x plus like 3x divided by whatever, right? I will ask you to find the acceleration at a specific point. You will also have an x and an y, right? So you plug in the num values for x and y here. But if it was parametric, you don't need to simplify. Okay? And to find the y component of acceleration, you essentially have to do the same thing. The only difference is going to be your equation. Let's write that equation here. I'm going to ask you to do this. I mean, hopefully I've already done this at home with your homework. Ay is going to be dv dt. Acceleration in the y direction is going to be the total derivative of velocity in y direction with respect to time, total. So it's going to be rho v, partial v, partial t, plus u, partial v, partial x, v, partial y, and w, partial v, partial z. This part goes to 0. This part goes to 0. And you'll be done. Any questions? No? Okay. Next question is also a homework problem. We are given an incompressible flow field horizontally in the xy plane with a velocity given by flows horizontally in the xy plane with a velocity given by u is equals to 30. U is equals to 30. 1 minus exponential of negative 4y divided by h meters per second, and velocity v is 0. So it's a one-dimensional flow field because v is 0. We only have u present here. Where y and h are in meters and h is a constant, just think of it as a number. We want to determine the average velocity for a portion of the flow between y and h. We had one equation for the average velocity, and that equation was integral of dv dA divided by a, right? In this case, we only have velocity in one direction. We only have u. So a small u average is the thing that we are looking for. Is going to be integral of u dA divided by a. The first thing you need to determine here in this type of questions is to what is this dA? So your velocity field, that's the velocity field on a plane. Let's say I'm not going to make any assumptions. Let's say it looks like this. And we want to find, and this is x, this is y. We want to find the average velocity from 0, y0 to y h. And it's a one-dimensional flow. This area represents the cross-sectional area. How can we calculate the cross-sectional area? We are not given any information about the depth of this field, right? And it's a one-dimensional field. So it is safe to assume that the depth here is 1 unit, right? It can be 1 meters, 1 feet, 1 whatever, right? In this case, we are dealing with SI units, so it is 1 meters. So your area is going to be 1 meters multiplied by H. That's the total area. So we can replace this with H. But this dA is a very small element of area. Let's say the area of this small stripe here, with the length dy. So this area is dy multiplied by 1, which simply means that this will transform to u dy. And we want to take this integral from 0 to h. Let's plug in the values and see if we can take this integral. Integral of 30, 1 minus e to the power negative 4 yh dy from 0 to h divided by h. This integral, this first part of the integral, is going to be equal to 30y minus. What is the solution to the second part of the integral? The part that includes the exponential. What is the integral of the exponential of e to the power x?
It's like 1 over derivative times.
1 over the power, right?
Yeah. So I guess for this one, it would be if we were trying to do like here, how would you derive into negative?
You don't need to derive it. It is 30 multiplied by 1 over the power, right? Which is negative 4 y divided by h, right? E to the negative 4 yh. That's actually, there's no y here. Just as you said, the derivative of the power. So negative 4 divided by h. Does this make sense? Do we already know this? How to take this integral? Okay. And this goes from 0 to h divided by h. You plug in the values for y. You plug in 0 here. This will be 0. This will be e to the power 0, which is 1. So I'm going to write it up here. We are going to get, let's put h first. We're going to get 30h minus 30. It is going to become plus sign. 30h divided by 4. E to the power negative 4 plus 1. And all of this is divided by h. Okay? Is there any questions? No. Let's move on. U equals to 30 square root of. Let's move on to the next problem. What is the next problem? Let's see. Time is up. Next problem tells us water at 0.1 meters cubed or cubic meters per second and alcohol with a specific gravity of 0.8 at 0.3 cubic meters per second are mixed in a void duct as shown in the figure below. What is the average density of the mixture of alcohol and water? So this is the void duct. We don't actually need to have the duct itself, just in case. This is the void duct. Water comes in here. Alcohol comes in here. Water and alcohol mixture goes out here. And we are told to find the average density going out. So row 3, let's call this 0.1, 0.2. So we have a row 1, which is the water density, row 2, which is the alcohol density, and we want to find row 3. The first thing you need to write down is the conservation of mass. So m dot 1 plus m dot 2, which are m in is equals to m dot out. How do we calculate m dot? M dot is equals to density multiplied by your flow rate, or density multiplied by a average velocity. Right? If your velocity is uniform, then this average velocity is the same as regular just velocity. If your velocity is non-uniform, you have to calculate the average velocity. But here we are not given any information about the velocity, so we're just going to assume it's uniform. I'm just going to actually use a row here, just Q here. So row 1 Q1 plus row 2 Q2 is equals to row 3 Q3. That's one equation. Rows here are different, and Q's are different as well. Okay. But there is another equation we can write for the flow rates. Since this flow is incompressible, the densities are changing because the liquid is changing, right? But we are still dealing with a liquid, right? It is not a gas. So we can safely assume that this flow is incompressible flow. So flow rate is also going to also remain the same. So Q1 plus Q2 is going to be equal to Q3 because we are dealing with an incompressible flow. So the point of this problem was to tell you that the liquids are always incompressible. It doesn't really matter if you're dealing with a mixture or not. The only thing is going to be for a mixture, we will have these two equations that are both going to be true at the same time. Okay? If in these pipes we only had water, we could have canceled all of the rows, right? Because incompressible flow, and then we could have concluded this. But since we have a mixture, we cannot just cancel all of the rows. We actually want to find row 3 as a function of Q's and densities. So let's plug this in here. So row 1 Q1 plus row 2 Q2 is equals to row 3 multiplied by Q1 plus Q2. Which means that your row 3 is going to be equal to row 1 Q1 plus rho 2 Q2 divided by Q1 plus Q2, right? What does this tell you? It tells you that this rho 3 of a mixture is going to be the weighted average of rho 1 and rho 2, and the weights are going to be the flow rates of each pipe. And since we are given the specific gravity, just something to make sure that we are on the same port, rho 2 is going to be a specific gravity multiplied by rho 1. So you don't need to have rho 2, just to make sure. I just want to make sure that we are all on the same page. Okay. Problem number 7. Do we have any questions? Problem number 7. We are given the, this is a Buckingham Pi theorem problem, right? It is telling us the excess pressure inside a bubble is known to be dependent on the bubble radius. Let me actually write this. And the surface tension. Okay. After finding the pi terms, we want to determine the variation in excess pressure if we double the radius or double the surface tension. So delta P, we are told, this is the excess pressure, is a function of R, the bubble radius, and the surface tension, sigma. Okay? So we want to find the pi terms. That's the first thing we want to find. And then we want to see how it would, how the pressure change, how the pressure excess changes if we double the radius or if we double the surface tension. Okay. The first step always is to count the number of variables you have. We have 1 variable, 2 variable, 3 variable. So your k is equals to 3. Then is the number of dimensions that are present here. The number of dimensions we have for delta P, we have newtons per meters squared. For R, we have meters. For surface tension, we also have newtons per meters squared. Okay, which that's newtons. Surface tension is newtons per meters. Newtons per meters. Right? If we write it, this is the FLT system. But if you write it in the MLT, do we remember what FLT and MLT was? Or do I need to go over this? Do we remember this or not? Yes. So we had 2 different sets of primary dimensions, either force length time, or force length or mass length at time. I usually prefer to use MLT, but you can use FLT as well. So in MLT, we are going for delta P, we are going to get mass divided by length times squared. That's for delta P, the dimensions of delta P. For length we are going to get just length, right? And for sigma, we are going to get mass times squared. That's the surface tension length, sigma. So how many primary dimensions are present here? All 3 are present, right? 1, 2, 3. All of them are present. So your R is going to be 3. So this will help us determine how many pi terms are we going to have. The number of pi terms. pi terms. 3 minus 3 is 0. Is this the correct conclusion? K minus R. Yeah. K is the number of the variables you have. 1, 2, 3. Right? No, not number of the pi variables, number of the dimensioned variables. R is the number of primary dimensions. This is going to be 0. Okay. So what should we do? Whenever you got to in this type of problem, what you want to do is to switch how you see your primary dimensions. Right? So instead of MLT, what I mean is instead of MLT, let's use FLT. Right? So let's use force, length, and time as primary dimensions. What will happen if you do so? The number of primary dimensions is going to reduce to 2, right? So this is a still R. So we're going to get 3 minus 2 equals to 1. Okay, so this means, what does this mean? This means that whenever, in general, if you were to use this Buckingham pi theorem idea anywhere, you have to check both of them, MLT and FLT, and take the maximum number. That will be the maximum number of pi terms you're going to get, right? But here, like in an exam, you don't need to do that. I give you the type of problems that will give you the consistent results. So you don't need to double check this. Okay. So what is the next step? We know we have one dimensionless parameter, and we want to find it. The dimensionless parameter is going to help us do the dimensional analysis, right? We are going to, the next step was to choose the repeating parameters and non-repeating parameters. But here we only have one pi term, so that doesn't really make any sense. Since delta p is a primary focus for us, we are going to assume that this is non-repeating parameters. What does this mean? It means its power is 1, right? It doesn't go to the power a or anything. So we're going to get delta p multiplied by r to the power a plus sigma to the power b. Does this make sense? Yes? Okay. And we have used the FLT method, so we're going to continue using the FLT method. Delta P in FLT was F divided by L squared. R is L to the power A. And sigma is F divided by L to the power B. Okay. Let's rearrange this. This tells us that F to the power 1 plus B here multiplied by the dimensions of this has to be at 1, has to be 0. And or 1 actually. That's all right. L to the power -2 plus A plus B has to be the dimension 1, which means that we are going to have the system of equations. 1 plus B has to be 0, and -2 plus A plus B has to be also 0. So B is going to be -1, and A is going to be negative. That's correct. Thank you. Thank you. Yeah, that was minus B. So we're going to get A equals to +1. So your pi term is going to be equal to delta pi multiplied by R divided by sigma. And this is a dimensionless parameter. So in our dimensional analysis, this will remain like constant if you were to compare two different cases, right? So let's answer the second part of this question. What will happen if we double the radius? If you double the radius to keep the pi constant, your delta p has to be reduced, right, by half. What if you double the surface tension? If you double the surface tension, double this, your delta p has to be doubled as well to keep the pi constant. Okay. We actually had a couple of questions here. Yeah, the handouts, I'm sorry, I'm just seeing this. They're asking whether the handout is uploaded on Blackboard. Yes, it is. Someone posted them in the group me if you're in there. Yeah, they were uploaded in Blackboard, and I guess they have figured it out. So they don't need my answer. And let me, it should be in the course contents. Make sure that I have uploaded. It is possible that I have forgotten about this. But we want to solve one more question, one more. So just give me a moment. Course content. I think I added it to the wrong course. I'm sorry. I will add it to the correct course with the solutions after the class, just in case you need the solution. I guess you already have had it. Yeah. And we are going to solve one problem. That's the problem number 8 on the homework. Sure. Problem number 8 on the homework. It is asking us to find the magnitude of the force F required to hold the plate in the figure below stationary. Okay. So we have this. I'll try to be quick, just to make sure we have not. This is your streams of water, and this is your plate. Have the direction of force F and 45 degrees. Velocity is coming in at 30 meters per second. M dot is equals to 5 kilograms per second. And we have V2 and V3. Okay. And we are also told to, we are not told anything about the coordinates, but the solution that I've posted, it will be posted in a couple of seconds, has taken this coordinate system, X and Y. If you take this coordinate system, you only have the force in the X direction, right? You don't have any force in the Y direction. But you can also take X and Y, right? That also works out. Okay, so we have the momentum equation. We can always start from the Reynolds transport theorem. dB dt has to be equals to sigma f, right? On the other hand, dB system dt is equals to, here B is actually mv, your linear momentum, mv of the system. And I'm mentioning the Reynolds transport theorem just to refresh your mind. You don't have to use the Reynolds transport theorem to get to the equation you need. You can just use the equation mv squared sine of theta, okay? Is equal to partial t integral of control volume rho v the volume plus the control surface of rho v vn dA. It's a steady condition. It's a steady case, so this is 0. So your sigma f is going to be equal to integral of control surface v rho v vn dA. Okay, we have fx and fy. Sigma f of x. It is supposed to be stationary, so sigma f of x has to counteract this force, the force of the linear momentum, right? On the, so integral of, let me actually write this, rho v, again, vn dA. We can write the same thing for the other direction. The idea here is that all of these velocities are constant. The same is true for density. So we can take them out of the integral. Fx rho v vn integral of dA is going to be a for all of these three surfaces. So surface 1, which is the inlet. So we are actually going to start with surface 2 and 3. Plus the same thing for surface 3 minus your inlet. Rho v vn a. And since we are only focusing on the force in the x direction, these velocities are going to be the x component of velocities. So that's vx1. In this coordinate system, v1 is only in the x direction. So that's fine, right? Then we have vx, this is vx1. Then we have vx2, right? Which is going to be this component of velocity. So vx cosine of 45. vx2 cosine of 45. And here we have vx3 cosine of 45. You can just plug that in, plug all of those in here. What should we do about this v dot ends? And this part is actually the main reason I wanted to solve this problem, because you hopefully have already done this for your homework, right? This v dot n tells us that we want the velocity that is normal to your surface, right? So we are looking, we don't really care which kind of component of force it is, which component of this momentum equation we are looking at. This is the velocity that is normal to the surface, right? This is your surface. What is the velocity that is normal to the surface? Is v2, right? So this will be v2. This part will become v3 sine or cosine of 45. This will become v2 cosine of 45. But this here will be the velocity normal to this surface. So this will be only v3, okay? This here will be the velocity normal to this surface. So this will be, this is actually v2, I'm sorry. This will be v3. And here we only have v1. Does this make sense? Okay. And then you can continue. You write the sigma Fy for the other direction. You should be able to solve the problem. Just the only thing that I really want you to focus on is this part, that when you're writing the linear momentum, this is the velocity in the direction of this force, whatever direction that is. If it's Fx, this is the velocity in the x direction. This, though, is the velocity normal to the surface, whatever that velocity is. So if you write this equation for sigma Fy, here you're going to get v2 sine of 45, but v dot n is going to remain v2. Does this make sense? Okay. And I guess we are out of time. Yeah, that's it for today. If you had any problems, please make sure to reach out to me. And yeah, I guess that's it. Sure. Yeah.
One thing is, for the homework, I sent you an email of the PDF that was supposed to be sent. In the Blackboard, I sent the wrong copy. That's all.
That's all right. Yeah, sure. Yeah, no worries. And for the online people, I'm going to make sure to submit upload the exam review right now. You have a question?